Welcome to Indian Perspectives, where culture meets science, technology, and a future full of growth. Join us as we explore India's rich heritage, groundbreaking advancements, and ambitious plans for a brighter tomorrow. Subscribe now and be part of this extraordinary journey.
Lithium Thionyl Chloride batteries are non-rechargeable, but they offer high and reliable performance and a long lifetime that makes them particularly well suited for IoT applications. But how do they work?
A battery is a system which stores chemical energy and converts it into electrical energy thanks to an electrochemical reaction. When the battery is connected to an external circuit, such as a communicating device, an oxidation-reduction reaction is triggered, releasing energy in the form of an electrical current.
A lithium thionyl chloride battery is made up of a negative material called the anode, the electron provider, which is made of lithium metal connected to the negative pole of the battery, a porous carbon mass where the reduction reaction occurs, a separator to isolate the negative from the positive materials, a positive material called the cathode, the electron taker, the thionyl chloride contained in the electrolyte, which is also conducting ions from the anode to the carbon mass, and a current collector connected to the positive pole of the battery. All of these elements are enclosed in a hard, hermetically sealed cylindrical casing. The lithium thionyl chloride systems are specific batteries, as the thionyl chloride is also the solvent of the electrolyte. Therefore, it is called a liquid cathode system.
One of the many advantages of these batteries is their high operating voltage, reaching 3.6 volts due to the nature of the electrochemical couple. The stronger the oxidation or reduction power in a given battery chemistry, the greater the resulting nominal voltage of this battery. For example, alkaline systems' nominal voltage reach 1.5 volts, while lithium thionyl chloride systems features 3.6 volts. Moreover, its voltage remains very stable during the discharge, which is unique and makes these batteries particularly suited for electronics applications. When you connect a device, it creates a conductive path and electrons start flowing outside the device. Positive ions generated at the lithium anode are transported to the carbon mass by diffusion within the liquid ionically conducting electrolyte. On their way, they cross the porous separator. This electrochemical process, taking place inside the cell, progressively consumes active anodic and cathodic materials over the whole discharge time, and eventually it stops providing electrons to the external circuit. That's how the battery dies. This can be quick or long, depending on how much energy is required by the device. Two other phenomena can impact the life duration of a battery: the self-discharge, and in the case of a liquid cathode system, the passivation. The self-discharge phenomenon is intrinsic to any electrochemical system, which leads to a loss of the battery's capacity. It is an internal chemical reaction consuming anode and cathode materials that is occurring during storage, but also while in use. Self-discharge is an important factor to consider for IoT applications, as the IoT devices must operate for several years with a single battery. One should distinguish between the following two self-discharge phenomena. Number 1, the self-discharge in storage, and number 2, the self-discharge in use. The self-discharge in storage leads to a decreased capacity of batteries during storage that causes them to initially have less than a full charge when put in use. The total storage time of a battery could go from a few months to more than a year. Indeed, lead times are piling up from the manufacturing date of the battery until its integration into the IoT device, and then until deployment and start of use. It is therefore crucial to consider the whole battery journey and take into account the self-discharge occurring at all these stages when estimating your battery's lifetime. The self-discharge in use is also important to anticipate, as this phenomenon occurs while the IoT device is in normal operating mode. Active materials are consumed as a consequence of another important chemical reaction in a thionyl chloride battery, the passivation. Both self-discharge phenomena are accelerated by external factors such as the elevation of temperature or the type of current profiles requested from the battery. For liquid cathode systems such as lithium thionyl chloride, another phenomenon is affecting battery performance: Passivation. Passivation is the main observable effect of a surface reaction that occurs spontaneously onto lithium metal surfaces in all primary lithium batteries based on a liquid cathode. This reaction corresponds to the corrosion of lithium metal by liquid thionyl chloride into lithium ions. It leads to the formation of a solid protecting layer, preventing further corrosion and, more importantly, avoiding any internal short circuit of the battery. This surface layer is called a passivation layer. It acts in a similar way to paint, protecting against metal corrosion. It protects the cells from discharging on their own and enables their long shelf life. The passivation layer is electronically insulating, which may have some detrimental consequences for battery operation. Therefore, its structure, morphology, and build-up over time must be properly managed. Indeed, internal resistance of the cell is enhanced due to the presence of the passivation layer, and this causes low voltage readings at initial times upon the IoT device's data transmission. After this rapid transient minimum voltage stage, diffusion of lithium ions through the passivation layer enables cell voltage to recover to nominal values. This second stage is called depassivation and is very important for efficient operation of the battery. The passivation phenomenon occurs at each data transmission of your IoT device.
Several factors are known to have an impact on the passivation effect, affecting the length and depth of voltage delay. Number 1, the lithium cell electrochemistry, construction, and manufacturer. Some chemistries based on liquid cathodes are far more prone to passivation than others. Nevertheless, within a given type of technology, some battery brands may display different levels of passivation. This is essential know-how in the toolkit of every lithium primary battery maker. Number 2, the storage duration. The longer the storage time before use, the more the passivation layer will grow, like rust on iron. Number 3, the temperature during storage and operation. The higher the temperature, the faster the passivation layer will grow and the bigger crystals will build up. While at cold temperatures, the passivation will grow more slowly, but the layer will be more compact. This is due to the fact that both electrical, chemical, and diffusion reactions are slowed down at low temperatures, and electrolyte viscosity is higher. Thus, the effects of passivation could be more likely visible, especially under high current draw.
Self-discharge and passivation's impact on the battery life is complex to model, and the potential disturbance brought by lithium passivation depends in some part on the application to be served by the batteries. Applications featuring a few milliamperes current draw, voltage cutoff below 2.5 volts, coupled with a few seconds allowable response time, will remain in practice passivation tolerant. Other applications with high current and voltage cutoff, frequent temperature excursions above 40 degrees Celsius, have more chance of experiencing a shorter than expected field life. And this is due to low voltage readings, even though there is remaining energy in the cell.
Don't forget to like, share, and subscribe to Indian Perspectives to stay connected and be part of our incredible community. Your support means the world to us. Let's explore, learn, and grow together.